In the previous lecture, we have seen the brief introduction of superconductivity. You know, superconductivity is a very important branch of solid state physics, and this most exciting field of solid state physics actually brought a very revolutionary change in the field of physics. Now from today, our aim is to discuss the basic concept of superconductivity. And as I have told you earlier in the introductory lecture, that we will divide our lectures on superconductivity basically in three categories. First of all, we will see the experimental survey of superconductivity, that is, we will discuss the different experimental results performed on superconductors. Okay? And after that, we will see the thermodynamic behavior and their explanations of superconductivity. And finally, there will be theoretical part when we will discuss the different theories to explain this quantum mechanical phenomenon. Okay? Actually, when you talk about superconductor, there is then one thing you must keep in your mind, that any material is not a superconductor, but there is a phase, there is a state of that material which exhibits superconductivity. That material will not exhibit superconductivity in any physical condition, but in a particular physical condition, you know, the material behaves like a superconductor. So we actually, superconductivity is a particular physical state under which the material behaves like a superconductor having zero resistivity. Okay? And so an indefinite current or infinite amount of current may flow through the material. Okay? So actually in the experimental survey of this superconductivity, first of all, we are going to see today a very important property of the superconductor. Actually, this property has been in brief dealt in the introductory lecture too, and this is regarding the perfect diamagnetism of superconductors. Actually, in the introductory lecture, I have introduced you that a superconductor actually behaves like a perfect diamagnet. Okay? Or you can say that a material in superconducting state exhibits perfect diamagnetism. Actually, this the phenomenon of perfect diamagnetism in case of superconducting state was first of all observed in 1933 by two great physicists, Meissner and Ochsenfeld. And so this perfect diamagnetism of superconductivity is also called Meissner Effect. Actually, what happens in this Meissner Effect and what is this perfect diamagnetism, or why we call a superconductor as a perfect diamagnet? Let us see. Actually, you can see this figure. That in this figure I have shown a sphere. Actually, this sphere is a material, and its temperature is greater than the critical temperature Tc. Okay? And you know, if the temperature of this material is greater than critical temperature, its resistivity rho cannot be equal to 0. There will be some finite resistivity of this material. Now, to behave this material as a superconductor, we start cooling it. Okay? And let us consider that material is being cooled, and finally its temperature becomes less than its critical temperature. You know, if this state of the material is a superconducting state, then definitely its resistivity rho will become 0 when its temperature becomes less than the critical temperature. But in this experiment, you can see I have placed this sphere, the superconducting sphere, in the magnetic field when its temperature was not below the critical temperature, or the material was not behaving like a superconductor. When T is greater than Tc, you know the material will not behave like a superconductor. And actually in that condition, we have subjected this sphere to the external magnetic field. And in this external magnetic field, cooling is started. And finally, we make the temperature of this material smaller than critical temperature. Okay. Okay. And now, when actually we make the temperature less than critical temperature, then we will see that you can see in this figure that no magnetic lines of force is passing through the material. Okay? It means this material excludes the total magnetic flux. No magnetic flux or no magnetic lines of force can penetrate this material when temperature is less than Tc. That is when the material behaves like a superconductor or it is in a superconducting state. But what happens when it is not in a superconducting state? It is just like an ordinary conductor. Then you can see in this first figure that the magnetic lines of force is passing through this material. Okay? But when T is smaller than Tc, that is the material now is in superconducting state, then no magnetic lines of force passes through this this material. Okay? So there is a complete flux exclusion observed when T is less than Tc. Okay? And if there no magnetic lines of force passes through the interior of this material, then definitely you can say the magnetic field inside this material will be equal to 0. That is, B is 0 or H is equal to 0 when T is less than Tc. Okay? Actually, this complete exclusion of magnetic flux by a superconductor, this phenomenon is known as Meissner Effect. This is known as Meissner Effect. And you know, a diamagnetic material actually repels the magnetic field or repels the magnetic lines of force. And if no magnetic lines of force passes through a material, such a material is called a perfect diamagnet. So here you can see this superconductor behaves just like a perfect diamagnet. Okay? Actually, and when, now see the figure, when the field is removed, then again your material will be in the superconducting state. It is already in superconducting state if you will maintain the temperature T less than Tc, or if you will make the temperature T greater than Tc, then it will become an ordinary conductor. Okay? Ordinary conductor. So in this first part of experiment, I have subjected the material to the magnetic field before cooling. Okay? Now let us see the second part of the experiment. In this case, this is your specimen of a superconducting material. Okay? But its temperature is greater than Tc. Okay? And no magnetic field has been applied. Okay? When T is greater than Tc. And you know, when T is greater than Tc, then its resistivity will be greater than 0 and it will behave like an ordinary conductor. Now its temperature is decreased, that is, the material is cooled, and its temperature is made less than the critical temperature Tc. So now in this material will be in superconducting phase, and its resistivity will become 0. But until now, no magnetic field has been applied. Now, once the material is behaving like a superconductor, that is, its temperature is made less than Tc, its resistivity is made 0, then we apply the magnetic field. So, the history of the material in the beginning, in the first set of experiment and in the second set of experiment is different, you can see. In this second set of experiment, no magnetic field has been applied initially, but a magnetic field is applied when the material already has started to behave like a superconductor, that is, its temperature has become less than Tc and resistivity is equal to 0, that is, the material is in superconducting state. Then this magnetic field is applied. Okay? And then it is again seen in experiment that no magnetic lines of force passes through this material, as you can see in this figure. Okay? So again, this material is behaving just like a perfect diamagnet. And when the magnetic field is again switched off, removed, then this material becomes just like a superconductor if its temperature is maintained less than Tc. Okay? So you can see this superconducting, you can see that the diamagnetic behavior of a superconductor is independent of its history, because in this condition the diamagnetic nature is exhibited by the material, you can see in the second set of experiment, when initially there were no magnetic field applied here, but in this first case magnetic field has been applied initially, but the final state or the diamagnetic behavior is achieved after applying the magnetic field in both cases. Okay? So the diamagnetic behavior of a superconductor does not depend on the fact that you have applied the magnetic field before cooling the material below its critical temperature or after this. Okay? So it is evident from this that the Meissner effect is a reversible phenomenon. This is just a reversible phenomenon. Okay? Now, as you have seen that the material in this condition under the magnetic field behaves as a perfect diamagnet, because there is no magnetic field inside the material. So you can say inside a superconductor the magnetic field B is 0. But this B is related to the magnetic intensity H by this equation. You know, you have definitely studied this. B is equal to mu naught times H plus M, where you know mu naught is the permeability of free space, H is intensity of magnetic field, and M is intensity of magnetization, or you simply say it magnetization. Okay? But as you have seen that this B is equal to 0 inside a superconductor. No magnetic field exists inside a superconductor. So let us take B equal to 0 here. So B is equal to 0, but B is equal to mu naught times H plus M, so that will be equal to 0. As mu naught is the permeability of free space, whose value you have definitely an idea that this is 4 pi into 10 to the power minus 7 Tesla meter per ampere. This is the value of mu naught. So it is a non-zero constant. So mu naught is not 0, so H plus M will be 0, and so H is equal to minus M. So inside a superconductor, you can see the magnetization is developed just in the opposite direction of the magnetizing field. If H is the magnetizing field, in against of H, magnetization is developed. So this is the direction of magnetization M, okay, which is just opposite. But the magnitude of the magnetization is equal to the magnitude of this intensity of magnetic field, okay. So what will be the susceptibility of this material? You know, the susceptibility is defined as ratio of the magnitude of magnetization and the intensity of magnetization, intensity of magnetic field H, that is chi is equal to M over H. But this M and H are equal in magnitude but opposite in direction. So taking the direction under account, you can say that this chi is equal to -1. So the susceptibility of this material is -1, and you know susceptibility of a perfect diamagnet is equal to -1. So a superconductor definitely behaves like a perfect diamagnet, okay. So the basic fact of Meissner effect, we have learned that in a magnetic field, when you will place a superconductor, no magnetic line of force will penetrate this material. And so the magnetic field inside the material will be 0. Okay. Actually, now we will see a very interesting fact that a perfect diamagnetic behavior of a superconductor cannot be explained simply by considering the zero resistivity. You know, rho equal to 0 is a very important property of superconductivity. But if your aim is to explain the perfect diamagnetic behavior of a superconductor, can it be explained correctly taking the fact rho equal to 0 under account? Answer is no. You cannot explain the perfect diamagnetic behavior of a superconductor to explain by considering that rho is equal to 0 for the superconductor. Only this fact is not sufficient to explain the perfect diamagnetism. How we can say that this rho equal to 0 is not the necessary and sufficient condition for the diamagnetic behavior of a superconductor? To explain this fact, let us consider now a perfect conductor, not a superconductor. So now consider a conductor, mark it, not a superconductor. And for this superconductor, this rho is not equal to 0. Okay. Now, when you will cool this conductor, you know, the resistivity of a conductor decreases, and let us consider that on cooling, this conductor becomes a perfect conductor. Mark it, this is a perfect conductor, not a superconductor. Don't be confused in superconductor and perfect conductor. Perfect conductors are not superconductors. Both are different things. Okay. So now you can say that we consider a perfect conductor. When you say perfect conductor, its resistivity will be also 0. Perfect conductor means that conductor which does not offer any resistance to the flow of electric current through it. So its resistivity will be also 0. So you can see rho is equal to 0 for both a superconductor and also for a perfect conductor. Okay, for a perfect conductor. But a perfect conductor does not behave like a superconductor in magnetic field. the behavior of a superconductor or a perfect conductor are different under the different conditions. You know, for a perfect conductor, rho is equal to 0. Okay. Now, from microscopic form of Ohm's law, you know, Ohm's law is expressed as E equal to, J equal to sigma E. Okay. And sigma is equal to 1 over rho. So this is 1 over rho E. And from here you can see that E is equal to rho times J. Rho times J. So E is equal to J over sigma or rho times J. But for a perfect conductor, as resistivity is 0, so this E will be also 0. It means you can say that in case of a perfect conductor, rho is 0 and by the application of this Ohm's law E equal to rho J indicates that no electric field can exist inside the perfect conductor. E becomes 0. Okay? And when E is 0, then what will be B? What will be magnetic field in case of a perfect conductor? For knowing the behavior of B now, we can think about Maxwell's one of the equations. You know, Maxwell's one of the curl equation is del cross E is equal to minus del B by del T. You know it. But you have seen that in case of a perfect conductor, the electric field inside the conductor is 0. And if E is equal to 0, then this del B by del T will be 0 and then B will be actually constant. B will be constant. So you can say that the magnetic flux density passing through a perfect conductor becomes constant. This B is called magnetic flux density. Okay? B is magnetic induction or magnetic flux density. Why? Because flux is equal to B dot ds integral. And so when you will define this B, this will be pi over area. Okay? And so this B is called magnetic flux density. Okay? And B is also called magnetic field or magnetic induction. Okay? So you can see that the magnetic flux density passing through this perfect conductor is constant. It means that when a perfect conductor is cooled in the magnetic field until its resistance becomes 0, the magnetic field in the material gets frozen in and cannot change subsequently irrespective of the applied field. And this is in contradiction to the Meissner effect. Actually, you can see this figure. From this figure, you can see that here I have shown there is a conductor whose resistivity is not 0. Now it is cooled and its resistivity becomes 0. Now this conductor is called perfect conductor. Now it is placed in this magnetic field. Okay? And when you will place it in magnetic field, then you can see that no magnetic lines of force are passing through it. Okay? And when the field is removed, then it is again in its original state. Okay? But now here you can see that the same specimen has been placed in the magnetic field initially. In this figure you can see. And then cooling is started. Now when you will cool it, rho will become 0, but in that condition magnetic lines of force is passing through it. Mark it. when you cool the conductor up to a temperature so that rho becomes 0 and then place it in magnetic field, then no magnetic lines of force passes through it. But when it is placed initially in a magnetic field and then you cooled it and make the temperature less than critical temperature, then magnetic lines of force is passing through it. Okay? And when this field is removed, then you can see the material is not in its ordinary state, but it just behaves like a magnetic dipole, like this. So actually, from this experiment, it is clear that the magnetic flux density passing through a perfect conductor becomes constant, and this means that when a perfect conductor is cooled in the magnetic field until its resistance becomes 0, the magnetic field in the material gets frozen, as I have told you, and cannot change subsequently irrespective of the applied field. And this is in contradiction to the Meissner effect. Okay? Actually, now we conclude that the behavior of a superconductor is different from that of a perfect conductor, and the superconducting state may be considered as a characteristic of thermodynamic phase of a substance in which the substance cannot sustain steady electric and magnetic fields. Hence, the two mutually independent properties defining the superconducting state are rho equal to 0 and perfect diamagnetism. When you say rho equal to 0, then E will be 0, because you know rho is equal to what? You have seen here, rho is equal to E over J. E over J. And so, if E is equal to 0, then rho will be 0. Or when rho is 0, you can see that then E will be equal to 0. Okay? And perfect diamagnetism, that means B equal to 0. Okay? So, this is all about the Meissner effect or the perfect diamagnetic behavior of a superconductor. Okay? Now, in the same line, we will see in the forthcoming lecture the concept of supercurrents and penetration depth in case of the superconductors. Okay? Thank you very much.